Welcome back. We just defined the Huffman extension of a code, and we also defined the Huffman contraction here. And they were just sort of in some sense inverses of one another. And we observed that any Huffman code for P is the Huffman extension of a Huffman code for P prime. And now we have reached the main step, the main calculation, which is the extension lemma. And the extension lemma says that if our code for P prime was optimal, then our code for P is also optimal if it's the H extension. So let's say that formally. Let P be a PMF with descending, with its probabilities in descending order, and let P prime be the same thing that it was before. It's all the same as the p's up to n minus 2, and then we just combine the last two, pn minus 1 plus pn. And our claim is that the Huffman extension to P, Huffman extension to P of any optimal code for P prime is also optimal for P. Any optimal code, the H extension of any optimal code for P prime is optimal for P. All right, so this is what we're going to show, and this is what we will need to prove the induction step. This is in some sense the induction step in the proof by induction that we're going to do. So let's prove this guy. Proof. So what do we need to do? We need to take any optimal code for P prime, and we need to take its H extension and show that that's optimal. So let's get started. So we first need to just let CO be optimal for P prime, And then we need to let CE be its Huffman extension, be its H extension to P. And our goal is to show that CE is optimal. So, for example, let's just write down our little example here so we can keep track of things visually. So let's say that CO is this guy. This is our running simple little example. That's CO, and then its extension, well, let's say, is 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1. So remember, in the extension, we take the last code word, and we just tack on a 0 to get one code word and a 1 to get another one. Okay, so that's well and good. So that's E, just an example, not the whole deal. And we'd like to show that this guy is optimal. So what do we need to do? Well, optimality is a statement about its expected code word length. So let's see if we can come up with an expression. Let's call it LE to denote the expected code word length of that. And maybe we can express it somehow in terms of the expected code word length of CO, since we know that's optimal. So we know something about its expected code word length. So let's just write down the definition here. I'll write it out sort of long since we're going to do some computations with this guy. So let's denote the lengths of the extension L superscript E. So we have these guys here. L E n minus 1 P n minus 1 plus L E n P n. Remember that the extension it has n code words, since the original one, the optimal one, had these n minus 1 code words, since P prime had n minus 1 elements. So what are these lengths in terms of the LOs? Well, we know that by the definition of the Huffman extension, well, I guess I didn't write it up there, the Huffman extension says, the length, so Li of the extension is just the same as the original length for all I, less or equal to or less than n minus 1, and then Ln is of the extension, or ln minus 1 is equal to the same. It's has the last two guys have the same length, and their length is this original dude plus 1. So it's ln minus 1 O plus 1. We just add 1 to the length of the longest, the previous longest, the previous final code word. So let's just plug those in here. So these are all the same. So we have L10 P1 all the same up to ln minus 2O Pn minus 2. And now this one is equal to LON minus 1 plus 1. Remember, this was LO, the length of this one, and it's one more. And same thing for this. So this is LON minus 1. Let's go ahead and distribute the Pn minus 1 plus Pn minus 1 plus ln minus 1 O Pn plus Pn. All right, and now we can see how to get the expected code word length of CO, right? Because we have all of its, well, not quite, I guess, so we have one more step here. If we want to get, what do we need to do? Oh yeah, so we're all good, right? This is LON minus 1 right here, and this is LON minus 1 right here. So when we combine those, so we're going to get, so this plus this is going to be LON minus 1 times Pn minus 1 plus Pn. If we combine those two terms, so what do we get? We get, over here, this whole thing was equal to LO, the expected code word length of CO, plus Pn minus 1 plus Pn. There was this guy and this guy. And all the others just get thrown into here. Okay, very good. So now we've got, so this shows us, we now have a nice little expression, pretty little expression for the expected code word length of this guy, the extension, in terms of the expected code word length of our original optimal code. Very good. But now, you know, we'd like to show that CE is optimal. So we'd like to show that this LE is minimal. And to show that it's minimal, well, we need to compare it against something that we already know is optimal. So let's come up with a new code which is optimal for the length n, for P, right? Because so CE here, this is on something that is on length n. This is on length n minus 1. So we could annotate these to denote, since this one's on the P prime and this one's on the P. Okay. So let's do that. Let's do another one. So this will be very similar. So this is sort of step 1 was this up to here. Now we have sort of step 2. So let's let CS. Now we're going to use our sibling code lemma, our key lemma. So we will let CS be a sibling code. Remember, a sibling code back up here. Here we go. Our key lemma, sibling code lemma, said for any P which had this descending order, then there exists an optimal binary prefix code with code words such that the lengths are non-decreasing. The last two are equal in length and they differ only in the last bit. In other words, it had these two siblings. So we know that there exists a sibling code on P. Remember, we were careful to put our P in descending order. So we can justifiably let CS be a sibling code, and by our definition of this implies that it's optimal. It's an optimal code in particular for P. Now we also, so now we're going to use the Huffman contraction. We use the Huffman extension. Now let's use the Huffman contraction. Let CC be the H contraction to P prime, rather, yeah, to P prime, write that clearly. So it's the H contraction of CS. And remember, the H contraction, the reason why one reason why we needed a sibling code was since the H contraction is only defined for a sibling code, right? We had to have these two siblings so that we could merge them, so that we could chop off their last bit and get a well-defined new code word. So we needed a sibling code here to get our nice contraction. All right, and now we're going to do something similar to before. So we're going to relate the expected code word lengths of these two codes, just very similar to what we did just a second ago. So let's do that. So let's write down, what should we do first? So we should do, we want to do the contraction. Okay, we want to do the expected code word length of the contraction. And let's write out, we'll use L superscript C for its length, and just like before, we're going to do this sort of thing. L C n minus 1, but now the contraction is on P prime, so it only has n minus 1 code words, and the probability of the last element is the sum of these guys. Now let's do something similar. Let's relate the lengths of our contracted code words and our other ones. So the lengths satisfy that the contraction, the length of the word for the contracted code is just like before. It's the same. Maybe let's write down an example here for concreteness so we can remember. So now we have the sibling code over here and the contraction, and we'll just use our same very simple example. 0 1 0 1 1 0 1 1 1, and these are our siblings. And the contraction, we just combine the two siblings, merge the two siblings. So we can see from this, make a little space, cut, paste. Then, so these are all the same for all I less than, my timer, sorry. Let's see, so what is this? The same, this one goes up to n, this goes up to n, so it's the same up to n minus 2, I less than n minus, strictly less than n minus 1. And then we have the contracted code word here, the n minus 1th guy, is just the same as this one, the sibling code minus 1 now. ln sibling minus 1. Right, this one has length 3. Each of these has length 3. Boom, boom. And this one has length 2. It's one less. Okay, so let's now plug those guys in over here. So what are we going to get? Well, these are all the same. L1 now S, L1S plus dot 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 plus L n minus 2 S P n minus 2 plus, let's see, maybe should we distribute this first, or just, let's see, yeah, let's distribute this and then we'll plug those each in. So if we distribute that and plug these in, we're going to get L n minus 1 S P n minus 1 minus P n minus 1 plus L n S Pn minus Pn. So I distributed this and I plugged this in for when it multiplied by the Pn minus 1, and I plugged this in for when it multiplied by the Pn. And then I distributed again the P's through each of these expressions. All right, and now we can see that, well, maybe, let's see, hopefully if it works, we should be able to, we're getting something that looks sort of like the expected code word length of our sibling code. So let's see. So we've got all the stuff up to here. The sibling code is on n elements. Our contraction was on n minus 1. So we've got that part, and we've got that part. So we are good. We've got ls. That's all this stuff. And then we're left over with minus pn minus 1 minus pn. So this implies we have the following expression for LC. The expected code word length of our contraction equals, let me do that in a different color, implies expected code word length of our contraction equals the expected code word length of the sibling code minus pn minus 1 minus pn. Very good. Alright, so looks like we're making progress. Now we annotated these to indicate the lengths of the, this one was for p, it was on length n, this one was for p prime, it was on length n minus 1, and now our sibling code was for p, so this is going to be a n, and our contraction was on p prime, so this is something on n minus 1 on p prime. Alright. Now, how can we combine these two? Well, we know this is an optimal code or this is a minimal, since this is C0, or CO was optimal. And we know that the sibling code is optimal. So maybe we can use that. So let's combine these two expressions. Well, it looks like a nice way to combine them, since maybe we can just cancel these guys with these guys. Let's add these two expressions, and those p's, those extra p's, are just going to cancel. So let's do that. So let me make a line here. So that was first. The first step was computing this thing. The second step was computing this thing, and now we're on step 3. Step 3, we're just going to add these. And what do we get? We get L, N, E. I'll drop the parentheses, maybe. I'll keep the parentheses. Plus L, N minus 1. Nah, it's sort of too messy. Okay, no parentheses on the ends. Plus this one equals, now I'm taking the right side, N minus 1 plus L, N, S, and the P's cancel. And now we know this is optimal, we know this is optimal, so let's compare those to since this may or may not be optimal, and this may or may not be optimal, let's get an expression. So since we know that the optimal ones are less or equal to those, we know, let's compare them. So L, how should we do it? Which way? Yeah, let's put the optimal guys over on the left. So we'll subtract those over, and so we're going to group the n guys together, so we'll subtract, no, I switched colors, S, N. And then we have the n minus 1 guys together, N minus 1, oh, that equals 0. Equals 0. So this is getting very interesting. Now, so what can we say? We have this is optimal for P, and this is the expected code word length of a code on P, right? This was the expected code word length of our extension, wherever it was. This was S was the expected code word length of our optimal. It was implicitly optimal, since any sibling code is by definition optimal. And this was our extension. So they were both on P, and now we're comparing CO is optimal for P prime, and CC is some code for P prime. So since the optimal one, like this one, is always less or equal to this one, that means that this quantity right here is greater or equal to 0. And likewise, this one since we're subtracting the optimal, this is greater or equal to 0. So we have a sum of two non-negative things, and their sum is 0. So that implies that each of them must be 0. So in fact, each of these is 0. This is equal to 0. I'll just put that implies they're equal to 0. And so that implies, right, because if one of them was not equal to 0, then you'd have some positive quantity, and it's not. So we know that LEN equals LSN, and LCN minus 1 equals LON minus 1. And what does this say? This says, since this was the expected code word length of an optimal code, this says that this code must also be optimal. It has the same expected code word length. That's what it means to be optimal. It has minimal expected code word length. And that's the expected code word length of our extension. And that is exactly what we wanted to prove. We wanted to prove that the extension was optimal for P. So this proves it, and in fact we also, in the course of doing it, we also got this other sort of side result here. Right, we got this bonus result that the contraction, here we had a sibling code, we took just some sibling code for P, and we also saw that its contraction, the Huffman contraction to P prime, is also optimal. So that's interesting. That's interesting too. But the one we really care about is this one, that the extension, the Huffman extension to P of any optimal code for P prime is optimal for P. All right, so this proves the extension lemma, and this is really, so at this point we've basically proved the optimality. We've set things up for the spike, and now in the next video we just have to, it'll just be a very easy proof by induction from here to show that Huffman coding is optimal.